Next topic is conductometric transducers or conductometric sensors. In conductometric transducers or conductometric sensors, the detection and determination of unknown concentration of sunlight is done by measuring the changes in conductivity occurring in a solution or in chemiresistive materials such as conducting polymers or metal oxides embedded with a sensing element. Okay, so here the unknown concentration of a solution we can measure, or gas, unknown concentration of a gas even we can measure, or a solution we can measure. It is directly either by the determination of a conductance of a solution or by the reaction of an analyte with the chemiresistive materials. How the conductance of a chemiresistive material affect by the reaction or interaction with the analyte. So two ways we can use. So this is the measure method we are using in conductometric transducers. Then you already know that conductivity occurring in a solution is due to the migration of ions. That is, the conductivity is mainly by electrolytic conductance. Then what are the factors influencing this electrolytic conductance? These factors also you already studied in your practical classes. So first factor which affects the electrolytic conductance is concentration of ions. So if more concentration, then conductance also very high, and also it also depends on the whether the electrolyte is strong, that means completely dissociated, or weak, which means partially dissociated. Strong electrolytes conduct more and weak electrolytes conductance is very low. Then the second factor is mobility of ions. So the mobility means how fast it traveled or distance traveled by an ion under a unit potential gradient. If mobility of a particular ion is very high, then again its conductance is very high. When compared to H plus and OH minus, H plus ions shows high mobility than OH minus ions. Then the third factor is temperature. As the temperature increases, conductance also increases. Then the final factor, fourth factor, is solvent. The characteristics of solvent, which means the viscosity. Highly viscous solvent conduct less, and also dielectric potential. If more the dielectric potential of a particular solvent, its conductivity is very high. So these are the four major factors, main factors which affects the electrolytic conductance. Then how we can measure the conductance of a particular solution? So the conductance of a solution is measured in using a conductance bridge called a Wheatstone bridge, which works based on the Wheatstone principle. So the typical Wheatstone bridge, it consists of an electrical circuit, and here the electrical resistance by balancing two legs of a bridge. For example, suppose R1, R2 are the two constant resistance, and the R3 is a variable resistance. We can adjust to using a resistance box. Then suppose the R4 may be the unknown resistance. So we can calculate the unknown resistance by bridging these four or these connections by an equation known as R1 by R2 is equal to R3 by R4. This is the typical construction of a Wheatstone bridge. So see here, R1 and R2 are the fixed resistance, and R3 we can change by using resistance box, and R4 may be the conductivity of an unknown solution. The conductance of a solution we have to know. So if we connect that external or unknown solution or by an external putting a conductivity cell, we can measure the conductance of particular solution. Okay. Then the conductivity of what is the components of a conductivity cell? The conductivity cell contains two parallel platinized platinum foils. Its area is 1 centimeter square area and are separated 1 centimeter apart, separated by 1 centimeter distance. And then again these foils are fused in a glass cylinder and connected to contacts connected with an external wire. Then alternate current is passed through this conductometric instrument, or alternate current of high frequency is used in conductometric titration, okay, to avoid polarization. Then specific conductance equal to the conductance measured into cell constant. So the specific conductivity we will obtain by multiplying this measured conductance into the cell constant. This cell constant is unique or constant for each type of cell. Okay, this is the conductance, how we measure the conductance of a particular solution. This is by Wheatstone bridge, and Wheatstone bridge, the fourth one, we can measure. It will be the unknown solution, concentration of or conductance of unknown solution. So what are the applications of conductance measurement? One of the major application of conductance measurement is the conductometric titration. Then by conductometric titration itself has lot of advantages. So first application of conductometric titration is it can be used for various type of titrations which is otherwise very difficult to conduct in normal way. For example, acid-base titration. If the acid-base titration, weak acid, weak-base titration, we cannot conduct by normal volumetric titration. So we can adopt conductometric titrations for that type of titrations. Even redox titrations, precipitation titrations, or complexometric titrations also we can conduct using this conductometric titration. Then even sometimes used when colored or turbid solutions are to be titrated, in which the endpoint cannot be seen by the naked eye. Okay, so see, these are some of the applications of conductance measurement, that is the conductometric titration. Then, in addition to the above mentioned applications, one of the major application of conductometric titration is the estimation of mixture of acids, titrating it with against a base. So consider a mixture of acids, HCl plus acetic acid. We can titrate it against NaOH, and we can also find the concentration of individual strength of HCl and also as well as the acetic acid. Okay, so what happened, you know that conduction of electricity through a solution is due to the movement of ions present in that solution. So we know that the known volume of base is added to the acid mixture of acids, it is neutralized. Okay, so first what happens is that if a mixture of acid contains HCl and both HCl and acetic acid, the strong acid is neutralized first and then followed by the neutralization of weak acids, because the weak acid is weakly dissociated, right? Its dissociation is further, and the dissociation is further suppressed due to the presence of H plus ion from the strong acid. This effect is known as common ion effect. So when we titrate a mixture of acids, one is strong and one is weak, the strong acid is neutralized first. Okay, neutralized means it is dissociated, it is in the form of dissociated. For example, HCl, then already it is dissociated as H plus plus Cl minus. So the extra H plus ion, the common ion which is present in acetic acid also consists of H plus and acetate ion. So the H plus produced from the HCl further suppress the dissociation of acetic acid. So complete ion neutralization of HCl occurs first, then only the neutralization of acetic acid will occur. Okay, this effect is known as common ion effect. So first HCl neutralizes, then HCl plus NaOH will produce NaCl plus H2O. So the fast moving H plus ions is replaced by Na plus ion. So what happened when HCl NaH is added to the mixture, the conductance first decreases. Then after the complete neutralization of strong acid, the neutralization of weak acid will start. So the first, initially the acetic acid is weakly dissociated. When it combines with the sodium hydroxide, then it converted to a strongly dissociated acetate and Na plus. So the conductance starts slowly increasing. Okay, so now the conduction of solution slowly increases with the addition of strong base. So then what happened when all the acid is neutralized, both the weak acid and the strong acid. Previously the strong acid get neutralized, now the weak acid also get neutralized. Then further addition of strong base causes steep increase in the conductance due to the availability of fast moving hydroxide ions. So the conductivity titration graphs look like this. Okay, first initially when NaOH is added to the mixture of acids, first HCl is get neutralized. So fast moving H plus ion is replaced with the Na plus, slow moving. So conductivity decreases. Then after the neutralization of strong acid, there is a production of strongly dissociated acetate and H plus. So again slow increase in conductance. Then again neutralization of weak acid. After the neutralization of weak acid, then again conductivity increases due to the production of OH minus ions. So from the graph, the first coinciding point or first intersection, we will get the V1, which is the V1 is the volume of NaOH required to neutralize strong acid. And from the second intersection point, it is called V2. And from the value of V2 minus V1, we will get the volume of NaOH which is required to neutralize the weak acid. So strong acid and weak acid, volume of NaOH we will get. From that volume of NaOH, we can calculate the strength of both the weak acid and the strong acids. This is conductometric titration. As I already mentioned, the conductometric sensors can be also constructed by using some chemi-resistive materials. So here the chemi-resistive materials is that which shows change in electrical resistance in the presence of a target material. So we can analyze some unknown concentration or unknown gas concentration or solution concentration by the adsorption of that substance into a chemical or chemi-resistive material, and which causes by the interaction of this material with the chemi-resistive material, it causes some change in electrical resistance in that chemi-resistive material, thereby using that change in resistance and thereby the change in conductance. We know that conductance is the reciprocal of resistance, right? So the change in resistance and thereby the conductance value is nothing but the indicative of the concentration of that particular analyte or particular target material. For example, we can construct a polyaniline based carbon dioxide sensor. So this type of chemi-resistive material is used for gas sensing applications. For example, polyaniline type material. Polyaniline is a conducting polymer. These chemi-resistive polymers can be conducting polymers or metal oxides, some nanoparticles, carbon materials like carbon nanotube, graphene. Also, all these substances can act as chemi-resistive materials. Chemi-resistive materials are those which shows change in electrical conductance or electrical resistance in the presence of a target material. So in the carbon dioxide sensing applications, which consist of polyaniline as the chemi-resistive material, it consists of a thin layer of this polyaniline film, which is lying in between a pair of coplanar electrodes supported by an insulating substrate. On the top of an insulating substrate, we can coat a thin layer of uniform polymer film, and in between two coplanar electrodes. So here what happens is that generally carbon dioxide is dissolved in aqueous solution. So dissolved carbon dioxide in aqueous solution, it exists as a weak carbonic acid. Carbonic acid means H2CO3. This carbonic acid again dissociated as bicarbonate and carbonate ion in basic solutions. So H2CO3 can further dissociate into H plus HCO3 minus, or again that HCO3 minus again dissociate into H plus CO3 2 minus. Then the solution or aqueous solution of carbon dioxide is mainly exist as HCO3 minus and H plus ion. So this carbonic acid doping, or this is called protonic acid doping of the insulated polyaniline, and it form the conducting counterpart. Okay, so if we add or if interaction of this protonic acid with the insulated polyaniline part, before interaction this polyaniline chemi-resistive material is insulating in nature, and after doping it with this protonic material, it forms conducting. So the increase in CO2 concentration results in the change of the pH of an internal electrolyte with the proton production. Then the conductivity increases of the doping of polyaniline by the protons. So what happens? The H plus and CO3 2 minus, or
CO3 2 minus, not H plus plus HCO3 2 minus, HCO3 minus. Here, see first the emeraldine base EB polyaniline is existing as like this, the first figure. Here the left part is conducting in nature, and the right there is a missing of that double bond.
Till now, we have discussed about conductometric sensors in which unknown concentration of an analyte, the unknown concentration of a particular solution can be determined by the decrease in decrease or change in resistance or conductance of a solution. And the conductometric titrations or conductometric sensing applications also can be done in the presence of chemi-resistive materials, in which that chemi-resistive materials like conducting polymers, metal oxides, that can interact with the analyte and produces a decrease in resistance or increase in resistance, and thereby that change, by measuring that change in resistance, we can found the concentration of an analyte. So what is meant by a chemi-resistive materials? These are those which shows changes in electrical resistance in the presence of a target material. So here the target material is maybe gas or maybe some ions in solutions, okay, whatever it is. So this chemi-resistive materials, by the use of this chemi-resistive material, we can sense different gases. Generally, the gas sensors, CO2 sensor is one of the gas sensor commonly used, common gas sensor. The sensing principle for polyaniline, for example, conducting polymer chemi-resistive material is very common. Among that, conducting polymer chemi-resistive material, polyaniline based conducting polymer chemi-resistive material is very common. So the sensing principle for polyaniline carbon dioxide sensor, the carbon dioxide sensor can be constructed using polyaniline as chemi-resistive material. It consists of a thin uniform polymer film on the top of a pair of coplanar electrodes supported by an insulating substrate. So a typical instrument look like this, or a typical set of gas sensing apparatus look like this. Two electrodes are there, which is coplanar, then it is on the top of a substrate. Okay, then polymer sensing film can be coated or made on the top of a substrate. Then here it can be used for carbon dioxide sensing. So the carbon dioxide first dissolved in water. So dissolved carbon dioxide in aqueous solution generally exists as a weak carbonic acid. Carbonic acid means H2CO3. See below there is an equation. CO2 plus H2O gives H2CO3, which is carbonic acid. This carbonic acid exists either H plus HCO3 minus, or 2H plus plus CO3 2 minus also there. So in basic solutions it exists as carbonate or bicarbonate. Then this protonic acid, HCO3 or H2CO3 is called protonic acid. So this protonic acid doping or H plus doping of the insulated polyaniline and form the conductive counterpart. So here the H plus doping in the before insulating conducting polymer, or if insulating polyaniline polymer, it is not conducting actually before doping. So the insulated polyaniline part, the polyaniline here used is emeraldine base polyaniline. So this EB polyaniline, this is insulating in nature, and after doping it converted to conducting polymer. So the increase in concentration of CO2 results in the change in pH of the internal electrolyte with the proton production. Then the conductivity increases as of the doping of polyaniline by the protons. So what happens, the reaction is given here. The first topmost portion is emeraldine base uh, polyaniline, emeraldine base polyaniline. When CO2 plus H2O combines, it forms H plus plus HCO3 minus. In the left side, addition of HCO3 minus occurs. Then what happened? The emeraldine salt is formed, ES polyaniline. So it convert from the original. There is a in the right side there is the conjugation is broken, right? Conjugation is broken, Then in the below that picture, the conjugation is regenerated, so it conducts the electricity more easily. So its conductivity increases as of the doping of polyaniline by the protons occurs. Oh, this is an example. So by measuring the change in conductance, or suppose before doping, some conducting polymers or some polymers shows less conductance or high resistance, and after doping its resistance may decreases. So thereby we can measure the concentration by these changes, by measuring these changes. The increase in conductivity reduces the resistance of polymer layer, and thereby concentration of CO2 can be measured. Here the absorption is the key and the first step in all the sensing techniques. The adsorbability of H2O and the CO2 onto polymer film influences the sensing properties and the working range of sensing materials. So adsorption is the first and key step in the sensing property. So if a polymer absorbs CO2 or gas, any other gases, it will perform good sensor. Okay, perform as good sensor. The last topic is optical sensor. Optical sensor is by its transduction signal is optical properties like absorbance, reflectance, transmittance, etc. So there are various kinds of optical sensors are there. One of the major it's commonly used optical sensor is photocolorimetric sensor or colorimetric sensor. So you have to know what is mean by this colorimetry, photocolorimetry, and photocolorimetric and all. And you already know about this very well. So for example, this colorimetric method, one of the example is which is given your in your syllabus, determination of ferric ion by or ferric ion by photocolorimetric method. And colorimetry is the based on the analysis of light absorption by a colored analyte species or by a colored compound of the analyte species that is generated by the addition of a reagent. So it is nothing but the absorption of light by a colored solution. So the basic principle behind this absorption or photocolorimetric method is, you know, that Beer-Lambert law, which is nothing but log I0 by I is equal to A, which is otherwise equal to epsilon Cx. Here epsilon is the molar absorption coefficient, I0 is the intensity of incident light, I is the intensity of transmitted light, A is the absorbance. And according to Beer-Lambert law, the absorbance value or light absorption capacity of a particular analyte solution is directly proportional to the concentration of that solution and also thickness of the cell. Here C is the concentration and X is the thickness. So log I0 by I, which is equal to absorbance, that absorbance is directly proportional to C and X. And the proportionality sign converted to epsilon X. Okay, if we transform this proportionality to a constant, it will give the epsilon. Epsilon is the molar absorption coefficient. Then you already know that photocolorimeter, in your practical classes you have studied this photocolorimeter, parts of photocolorimeter, etc. Then you have to study for your theory also. Then estimation of ferric ion by photocolorimetry. So first we need to convert that Fe3 plus into a complex called ferric thiocyanate. Here it is SCN, not CNS. Okay, SCN 6 times 3 minus. Then that it absorbs light in the almost the region is 400 to 700 nanometer. Exactly the range is 480 nanometer, which is given in your procedure. So if the concentration increases, the absorption of that solution is also, absorption of light is also increases. In addition to the potassium thiocyanate, we need to add HCl also in order to prevent hydrolysis. Then you need to construct a calibration curve to determine the unknown concentration. The calibration curve prepared by using, first we have to prepare different standard solution, then measure the absorbance of each standard solution and plot its absorbance against the concentration. Okay, plot a graph. then from the graph we can measure the absorbance of unknown solution, and from the graph we can find the concentration of unknown solution also. Okay, so this is your photocolorimetry and photocolorimetric method. So that's it.